let us make the acquaintance with the first kind of differential equations that we'll be looking at in some detail. Turns out, and as we're going to find out in the next class, that this is just one example of a more general type of differential equations, but I'm getting ahead of myself, so I'm not going to do that. So in the last class, we looked at the fact that a differential equation that looks like the one that you have in front of you is called an exponential model. And in fact, this is used when we can apply to any phenomenon where a quantity y changes, usually in time, but doesn't have to be, but changes at a rate proportional to its current size. And now, the question is, what is exponential about this model? You see in front of you the graph of an exponential function, actually the standard exponential function, and what does that have to do with the original differential equation? There doesn't seem to be any exponentials in there. Well, turns out that the solution does. Turns out that the solution of a differential equation of this type, y prime equals ky, where k is a constant, is actually an exponential function of the form c times e to the kt, where the k that you see there is exactly the same that appears in the original differential equation. Why, you wonder? Well, here is why. So how do we solve an exponential ODE? What we're going to do is we're going to use a good old trick that we've used several times in differential calculus, and that is to treat the Leibniz notation for a derivative as if it were a real quotient. So we start from our differential equation, but written as dy by dt equal ky, and then we're going to pretend that the left hand side is a real quotient. We're going to cross multiply, and we are going to rewrite that equation in this form: y over y dy equals k dt. Now when you think about it, the left hand side is actually a differential in the variable y, while the right hand side is a differentiable in the variable t. Now you'll notice that there are a few technical items here that really need to be checked out. We're not going to do that. Again, we're not too interested in the minute technical details. But one of the details is, of course, the fact that we have cross-multiplied, even though, in fact, the Leibniz notation is the notation for a derivative, not a real quotient. The other one is that I'm saying that the left-hand side of this last equation is the differential of some function of y, although y is the function itself that we want to find out. But again, we're thinking of y as a variable. Okay, it depends on its own on another variable t, but you can think of it as a variable as well. Anyway, again, there are some technical issues that need to be checked, and believe me, people have checked it and they work out. Now, assuming that all this is true, then if those two differentials are in fact equal, that means that the original functions that they came from, they have to differ by a constant, right? Remember, after all, the differential is just the product of the derivative times the differential of the variable. So if those two are the same, that means that the original function have to be different by a constant. All right, what are the original functions? On the left hand side, we're looking for the integral, or the indefinite integral, or the antiderivative of 1 over y, and on the right hand side we're looking for an antiderivative for k. Well, they're both very easy, and we know that the left hand side gives us the logarithm of the absolute value of y, and the right hand side gives us kt. But remember, now we've integrated, and those two are supposed to be different by a constant, so we need to add that constant. Okay, so far so good. Remember what we're looking for. We're looking for y. We want to express y as a function of t. So what we're going to do is take the exponential on both sides, which has the effect of removing the logarithm of the left hand side and bringing the kt plus c to the exponential. Now you can see where the exponential comes from, right? Furthermore, we can write the right hand side as e to the kt times e to the c. So we're separating the variable part with the constant part. But remember, what we're looking for is not the absolute value of y, we want y itself. Well, the absolute value just takes away the plus or minus, which means that y is actually going to be equal to plus or minus e to the c, e to the kt. But let's think for a minute about it. What's e to the c? Remember, c is the arbitrary constant that we added, so it can be any number whatsoever. Once we take e to the c, we end up with any number, well, not quite, any positive number. Well, the plus or minus simply allows us to include in this general family of functions all the functions where the coefficient in front is any positive or negative value. But look at the original function. If y is equal to 0, that works as well. It just gives us 0 equals 0. So that means that plus or minus e to the c really can be any number whatsoever. So we might as well change it to just an arbitrary constant. Just to emphasize the fact that this new constant is not the same as the one before, we're going to write it as a capital C. Okay, but here it is. This is the formula for the solution. We came all the way through the equation by doing steps again with some technical details that may need to be checked out, but overall you can see that it's pretty solid, and therefore that means that our the solutions of our differential equation will be always of the form some constant c times e to the kt. Now notice before we move on that the plus c, there was that constant we kept adding, and I keep telling you that you have to add it, absolutely no exceptions. In this case, when we're solving this problem, ends up being not a plus c, not an added term, but in fact a coefficient, a multiplicative constant. Keep that in mind, because as we move through other differential equations, you'll see that constant popping up or ending up in all kinds of strange places. And again, we need to keep track of where it ends up, because that makes a big difference as we're finding the general solution of the equation.